Welcome back to ECE 442-542. If you're just now seeing this page, there's a lot of announcements, but I know you have a week coming up that you may not have anything to do, so I thought I would provide you with some opportunities to continue to work during that what's apparently labeled spring break. But we have two more lectures prior to that. The reading assignment, now we are starting Unit 4, which is discrete equivalence. In the textbook, that material is actually distributed over a couple of different chapters. Chapter 3 deals with zero-order hold equivalence, which is what we will discuss today. And another version of discrete equivalence, which we will call numerical integration techniques and pole zero matching or pole zero mapping, are done in Chapter 6. That's the sections in the course textbook that you can refer to if you want to see additional material beyond what I'm providing here, which is what I would recommend that you do. There's also going to be additional lecture material. It's not extra, it's additional, meaning you need to look at it. And it will be discussing particular examples that we may not spend time with in class on zero-order hold equivalence. There's going to be one, which is Lecture 4.2, that contains a table. It's not a straight Z-transform table, it's a table of zero-order hold equivalence. And hopefully that will become more clear what that might mean after today's lecture. Today we're going to try to give an overview of discrete equivalence. One such strategy is a zero-order hold equivalent. Lecture 4.3, it has an A and a B, but that's dealing with this concept of zero-order hold equivalence with state space representation. We'll be discussing it in class with transfer function descriptions. 4.3b is actually an example of doing that. So you have two different sets of lecture material that's additional that I haven't provided until after this particular lecture is made available to you. I didn't want you looking at that and saying, I have no clue what they're talking about or what this represents. Hopefully after today's material, that will become a little bit more clear. Some of you are still sort of struggling or trying to figure out the last problem on homework number 3. That deals with Z-transforms of complex poles. There is some additional notes, not a video, just notes showing you two different strategies to do the same thing. One is with respect to using complex numbers, and one is with respect to using real numbers in your derivation of inverse Z-transforming complex poles. All of that is due tonight, but there are hints for problem number 4 on D2L. Exam number 2 is not this week, and it's not, I think, the week after spring break, but it's in a few weeks. It's on the 25th of March. And if you're in 542, today I posted the project description. So now you have a few weeks to think about what you want to do for your project. The first deliverable is due on April 1st, and that's not an April Fool's joke. It is when deliverable number 1 is due, and really deliverable number 1 is a 2 or 3 sentence description of what you're wanting to do for your project. But I want you to give it some thought. That's why I have a deliverable. Deliverables number 2 and 3 are due at the end of the semester, and that's basically your write-up and a reflective paragraph. That's deliverables 2 and 3. But look at the project description, and if you have questions, we can talk about that later. Today what we want to do is start Unit 4, which is discrete equivalence. I'll try to give an overview, and then we will go through zero-order hold equivalence, the derivation of that, and hopefully get through a couple of examples. What's forthcoming is numerical integration based discrete equivalence, which will probably be after spring break. No, actually, it will be Wednesday. I've lost a lecture. So between today and Wednesday, you could do lecture 4.2 and 4.3. Those are all based on zero order hold equivalence. The lecture on Wednesday, or the next lecture, will be on numerical integration strategies for discrete equivalence, and then probably after spring break we'll talk about pole zero matching or pole zero mapping strategies for discrete equivalence. Discrete equivalence is not a new topic, and I tried to color code this, but it may be hard to see. I have a blue, a black, and a green. But discrete equivalents are really trying to go from an h of s to an h of z, or a c of z to a c of s to a c of z, or a g of s to a g of z. We're trying to find discrete equivalence for where h of s might be a filter. Think low-pass filter. How do I make a discrete time transfer function if I now know what my continuous time transfer function looks like? What if I have an analog controller or a continuous time controller called capital C of S, and now my boss, she wants me to put this on a computer. She needs a discrete controller. Can you now produce a C of Z, a discrete equivalent to the C of S? How do you go between these different domains? And finally, which is really what we will focus on mostly today, is when G of S is a plant, a system that we're trying to control. Can we now model that by a G of Z? And in that case, it's going to be a little bit more elaborate than a straightforward discrete equivalent from h of s to h of z, or c of s to c of z. Those two can be thought of in the same way. The last one is the zero order hold equivalent that we will focus on today. Or you could be dealing with the following question. What's behind the function in MATLAB called C numerical 2 letter D? Continuous to discrete. That's simply a function in MATLAB, and we will be giving you or providing you information for what it means if you put in a different argument in that function. You now say matched, or you say tungsten, or you say forward. There's different arguments you could put into that C to D function to tell it to do one of these types of discrete equivalence. If you leave that descriptor out, it by default will perform a zero order hold equivalent. And if you want to learn more about that, you know how that's done. You simply say help C to D in MATLAB, and it will give you that information about that particular function in MATLAB that does this. So you now have ways of finding the answer in the back of the book. You can now pull up MATLAB and produce the answer for these homework problems that you are being asked to do, maybe by hand. And in some of those, you're actually allowed to use MATLAB to produce that. I want you to know how to make that happen. To get us started, if you haven't had a continuous time control system, that's not that critical, but here is a block diagram of a continuous time control system, and it has a lot of different inputs associated with it. We could have the reference input, R of S, which is maybe the command that says go to 10 degrees. You might have a disturbance input that might be a wind. Let's say you're trying to control a sailboat and you're wanting to go from point A to point B, and now you have this wind at some weird angle impacting your dynamical system. That's this D of S. Or maybe you have noise in the system that's coming in or added to your output sensor variable that you're measuring. This now gives you the overall sort of block diagram description of a plant that's controlled, and a lot of times we simply have or assume that that feedback dynamics is unity. Capital H of S may just be 1. We measure Y, and I might say, oh, we have unity output feedback. Then Y is just coming straight back and being compared to the reference input R. That's the analog version. What we are doing in this class is discrete control. So how do we now introduce the discrete control ideas or concepts relative to this configuration or this particular scenario? And there's two different ways: situations, scenarios, reasons for discrete equivalence. We can convert controllers or filters from a C of S to a C of Z, meaning now we want to pull out that all analog controller that might have been a bunch of op amps, resistors, capacitors. We want to extract that from our control system and then put in a microprocessor or a microcontroller or a computer. We want to convert from C of S to C of Z. And in that case, you can sort of envision what that might look like here. Now you're trying to get rid of that C of S block. So you now have to interface that controller with a discrete implementation, which means somehow you're going to have to sample that air signal and probably inject a sequence of numbers into that system. Well, how do you do that? So we'll talk about that. That's one reason for a discrete equivalent. The other reason is if you actually wanted to do design or analysis, you wanted to design a discrete time controller based on a discrete representation of your system. So now you need to somehow convert this plant into a discrete time version. Go from a G of S to a G of Z. What do those look like in block diagram form? These are simplified block diagrams because I don't show you the disturbance, I don't show you the noise, I don't have any feedback dynamics. Capital H of S is 1, but I'm just trying to focus on the particular aspects that are important to us. Here is scenario number 1, or reason number 1. We want to convert from this all analog controller that's maybe a bunch of op amps and resistors and capacitors all interconnected, and we want to replace that with a computer or a microprocessor. We need now a C of Z that will allow us to program that controller's functions into a discrete implementation. We have to interface that with the original plant, which is analog. We're keeping G of S. So we're trying to keep the input U of S the same. That's the same. We now have, if G of S is a motor, we can't control that motor with a sequence of numbers. We have to inject into that motor a continuous waveform. U of S has to stay as a U of S. The output of that system is still an analog signal, but now we are comparing that with an analog reference input. We're generating an analog air, but now we need to somehow get that analog air into our controller. We need to sample it, or we need to go through an analog to digital converter. Now we have a sequence of these air signals. We process those through our controller, and now the controller is just putting out a sequence of numbers, which doesn't make any sense to a DC motor. So now we have to somehow convert that discrete sequence of numbers, go from a digital to an analog signal. That's the D to A, the digital to analog conversion. So that A to D and D to A we need to worry about, but we would have those in place. All we are doing is converting that analog electronics and replacing it with a digital system. C of S to C of Z. That's reason number one. Or you could view that, so now you're finding C of Z, a digital implementation, it is a discrete equivalent of C of S, or maybe now somebody hands you an analog filter from ECE 320, or now you've designed one. You now have this Butterworth low-pass filter, H of S, that's your buddy, that's your favorite, and now somebody says, oh, I actually need you to put that into a computer. I want you now to reproduce that filter's behavior with a set of difference equations, so that I can now give you a sequence of numbers, and you can now filter that by processing those through this digital filter. That's this second scenario in the cloud, but that's finding D of Z, which is a discrete equivalent of an H of Z is a discrete equivalent of H of S, where H of S is your favorite analog filter. Here's the second scenario. Now we're actually doing everything in the discrete setting. Look at the output. That's now the Z transform of a sequence of numbers. That's capital Y of Z. We actually are using a reference input that's a discrete sequence of numbers, which in the frequency domain is now R of Z. C of Z is now a discrete controller, and we'll learn how to design those in this class. But now, before we can do that, in order to design those, we have to have a capital G of Z. Somehow we now need to turn this analog plant, this robot arm, this DC motor, this vehicle, this mass spring damper system, this chemical plant, whatever G of S is, we now need to convert it into a G of Z. And the way that we will do it is we will actually incorporate the behavior of the D to A and the behavior of the A to D and put all of that together to obtain our G of Z. And that's what we will call a zero order hold equivalent, because our D to A will be a hold and it's a zero order hold. All that really means is if I give you a number, you hold that number fixed or constant. It's a zeroth order. It's not sloping. If I hand you a 2.2, you say, okay, I'm just going to give you 2.2 as a signal during the entire sample period. Then at the end of that sample period, I hand you another number, and it's now 2.7. And you go, that's fine. I'll just now hold that 2.7 constant for the next sample period. That's the behavior of a zero order hold. And we want to incorporate that together with G of S and this sampler, this A to D, and package all of that into a G of Z. That's a little different than simply starting with an H of S and getting an H of Z. We're not putting any D to A and A to D into that conversion, or it's a little, and that conversion is the same as me giving you a C of S and asking you to give me a C of Z. Again, we're not incorporating the A to D and the D to A behavior into those discrete equivalents. I know this is probably a little bit, what do I want to say, fire hose-ish. I'm feeding you with a fire hose, but eventually you'll start to get a feel for the distinction between these discrete equivalents. We're going to have a lot of them, and you'll start to understand why we might use one versus another, and why we have options. Question? So now in this conversion, in reason number 2, in this discrete equivalent scenario or situation, we are incorporating the D to A and the A to D. We're packaging all of that together with G of S to produce a capital G of Z. We're figuring out how those are influencing G of S, and now the result is a capital G of Z. So that now if you're analyzing this block diagram, you have two system transfer function, a C of Z and a G of Z, and everything that's happening is a discrete analysis. That's scenario number 2, or reason number 2, and we will call that more specifically a zero order hold equivalent, or a ZOH equivalent. And that's what we're focusing on today, is how do we do that? How do we make that happen? We now want to find a plant in the discrete time setting, a capital G of Z, from an analog plant, G of S. Just think of a first order transfer function, 1 over S plus 1. What does that look like if I find its zero order hold equivalent? What if we even make it easier and we say, what if our plant is just a constant? Our plant is now 5. It's just a gain. What does that look like as a zero order hold equivalent? What if our plant is an integrator? It just takes a signal and integrates it. What happens if we now put an integrator in for G of S? What does its discrete equivalent look like? That's what we want to look at now. Let's examine the process for obtaining G of Z from G of S. And in particular, it's this now zero order hold equivalent, or reason number 2. We want to find capital G of Z, which is really this ratio of the Z transform of the output over the Z transform of the input. We have an analog plant. We have, on the input side, a digital to analog conversion going on. At the output side, we have an analog to digital conversion going on. We want to package all of those properties into this discrete equivalent, which we are calling capital G of Z. And the way that we're going to do that is we're going to break it down into different pieces. We know G of S. We're going to assume that we have G of S. That's now our plant. Maybe that's an integrator. Maybe it's a first order system. What does the zero order hold and what does the A to D look like? What are its properties? Let's examine those now. We're going to look at the analog to digital, the output side, and the digital to analog, the input side, the zero order hold side. And we'll look at those. You would expect those to be different. One's going analog to digital. We're sampling. What does that look like? The other one goes from digital to analog. And we'll do a zero order hold. Do you remember what that is? I hand you a number and you just hold it. Hold it fixed. I give you 1.6. You say, okay, 1.6 as an analog signal during the length of time of your sample period. I now hand you the next sample, which is 1.8. You just say, okay, 1.8 from now until the next sample. That's our zero order hold. I'm not trying to do any slopes. That might be a first order hold. If I said, oh, I'm trying to anticipate, I need a slope, first order hold. No, we're just doing a constant, a zero order hold between the digital to the analog. So let's look at the first one, the output side. I've already given it away, but if you were watching as I was sliding, here's the analog to digital characteristics. We have an analog waveform at the output, which I'm calling Y of t, and we want to sample that. And we're sampling it at t, 2t, 3t, 4t, etc. And just assume that those are precise equivalence between the values of y of t and what I sampled there with my drawing over on the sampled side. Use your imagination if they don't look quite the same, but they're supposed to be the same numerical values. I'm not worrying about quantization effects. I'm not assuming that I'm worrying about how this gets quantified. I'm saying I have a infinite resolution. I'm just worrying about what is the value of y at each of these instances of time. Capital T, capital 2t, capital 3t, etc. What's the relationship, or what are the properties? Are there any dynamics in this? I now have y of t at time 0. Let's say it's 6. What do you see at the digital output side? What's y of 0 in the discrete time setting? 6. Let's say at capital T, it's now 7.2. What is it at the digital side? 7.2. Is there anything going on? No. There's no dynamics, and for that reason, there's no memory. And essentially, we don't really need to worry so much about the properties of this analog to digital conversion process. That's not really impacting us at all in terms of when we put it all around g of s. That's not going to do anything different to our system. Zero order hold is a different story. And this is what we have to do on the input side of our plant. Our plant is an analog plant. It cannot respond. If you took a DC motor and applied to that at time 0, 2, and then at time 0.001, which is the next sample period, and you said 2.1, and you just did it 2, and then you quit, and then you said 2.1, it's going to go, what is going on? It won't respond. It needs an analog waveform. We are now making that happen by simply holding that constant in between sample periods. If you now had a sequence of numbers, which I'm referring to now as u of n hat, given this sort of up and down shape, it would now look like this stair step, this uneven step picture, when it's now on the analog side. I'm just holding constant between each of these values at each sample instant. We now need to figure out, okay, how do we model that? Can we model that? What's the time response behavior of this zero order hold? And one way to find that is to go ahead and apply, question? I'm not sure I understand the question. Go ahead and... So now we're doing a zero order hold, which just means that we are not anticipating or trying to predict what the value is going to be at the next sample period. We're just holding it fixed at what we know it equals at the present time. If we said, let's say that u of n hat is now 2.7 at 0. We will just hold it at 2.7 until we get to that next one, which let's say is 4.
So can you change the order so that you do predict it? Is that what
So now higher order filters, the question was, can you change the order to maybe be more anticipatory? Yes, you can. That just complicates the process of going from g of s to g of z, and it may not add any benefit. It may actually be worse. So now if you have a signal that's not that predictable and you can't anticipate the slope at the present time, you're going to maybe be in error in the wrong direction. So let's just sort of say, let's not try to anticipate, let's just do a zero order fit to that signal that or that signal's value that we know now, and just hold it constant.
So for zero order hold, for the most part, it's most effective?
So for us, we are choosing the zero order hold, one, because it's probably the most straightforward to analyze, and it's not necessarily going to damage us too much. It basically introduces a little lag into our system response. And if you've had a control class in the past, you know that lag is not good. It is deteriorating your ability to control the system a little bit. But we'll overlook that for now. What we want to do now is find the time response behavior of a zero order hold. Suppose we apply a unit pulse, a value of 1. I give you a 1. What's the output of the zero order hold? Here's time. And let's say that I now apply a value of 1 at 0. This is now what I'm going to call G sub zero order hold of t. What does it look like for that one sample period interval? It's just flat, isn't it? It's just 1. This is now our time response behavior of a zero order hold. Can we describe that with elementary waveforms? Can you now give me an expression for G sub z OH of t in terms of elementary waveforms or functions? So now we're actually in the analog setting, aren't we? So somebody was saying U of n, but I'm going to say it's analog. And I'm assuming you're meaning U now is not a generic input, but that's the unit step. The unit step, U of t, what would that look like? Well, that would just be this, wouldn't it? That's not quite what we have, but you are getting there. We now need to turn it off. And we can do that by saying, well, just subtract a unit step of the same amplitude, well, unit, so it is the same amplitude, one time sample later, U of t minus capital T. I've delayed the unit step, one sample period, and I'm subtracting that from the traditional elementary signal U of t. This is now my time response behavior of the zero order hold. Here is the unit step. This is the unit step delayed by one sample period. And this is really what I was after. This is now the, well, let me call it the unit pulse. This is what would come out of a zero order, or this zero order hold, or this D to A operation would be the unit pulse of a zero order hold. I inject a pulse. I hit it with 1. And this is what you see. It's 1 for one sample period, and then it's done. That's the time response, or the unit pulse, of a zero order hold. Similarly to an impulse response in an analog system, but now this is a unit pulse because we're hitting it with a value of 1. Yes?
So this is the analog domain. What was the digital domain? Was it just hitting it with 1?
So now, this right now is the analog. We are finding the analog form of this D to A because we need to now figure out how to get this discrete sequence of numbers, U of n, converted into a continuous time form that will drive our analog plant. Right now we're worried about, can we model this zero order holds dynamics and package that together with what we know G of S is, package that also with the A to D, put all of those pieces together to create this capital G of Z, our zero order hold equivalent. And the A to D we kind of don't need to worry about. That didn't have any dynamics. That didn't have any memory. The zero order hold, I think you can see, that has a little bit of character. You now hit it with a 1. It gives you a 1. It has memory. It holds on to that value for one sample period, capital T. And now we've described it in the time domain, which I'm hoping now allows you to put that into the frequency domain. Because we really want to package a frequency domain version of that zero order hold together with capital G of S. Because if we have them both in the frequency domain, we can multiply them together. Don't have to worry about convolving in the time domain. We want to do it in the frequency domain, and that's this product of terms. What's the Laplace transform now of the right-hand side? The left-hand side is easy. We just capitalize the lowercase g. We now say, okay, what's capital G sub ZOH of S? What's the Laplace transform of a unit step? That's 1 over S. We take away from that the Laplace transform of a delayed unit step. So we have a unit step. Do we have to modify that? Yes, because it's delayed, and the delay is this e to the minus capital TS. Or we can now factor out a common factor, which is 1 over S, and we have 1 minus e to the minus TS times a 1 over S. Or we could say, oh, the S is in the denominator, and upstairs we have 1 minus e to the minus TS. Pictorially now, we have a frequency domain representation of that zero order hold. It's now this 1 minus e to the minus t over S over S. And if you're thinking back to Laplace transforms, you go, oh no, now I have an irrational expression. I'm not used to dealing with an irrational expression involving e to the minus ts. Well, the nice thing is that's very specific in terms of what that looks like in the discrete setting, because that's the delay of one sample period. This now we could say is, let's say, y sub 1 of s. Now we can put those pieces together. It's 1 minus e to the minus ts over s times g of s. where this is now the Laplace transform of the unit pulse of whatever system we start with, capital G of S. Now, if you hit that zero order hold plant combination with a pulse, a unit pulse, this is what that will look like in the frequency domain. It will be y sub 1 of S. Yes? So it'll hopefully this will start to become a little bit more comfortable. Believable, let's worry about comfort first. So now we have y sub 1 of S. What is that? That's now 1 minus e to the minus ts times g of S over S. Haven't done anything except just rearrange the S. Or I could write y sub 1 of S as g of S over S minus e to the minus ts g of S over S. So you can kind of see that I might be needing to find something associated with g of S over S. And what is that really? That's just the original system with one more pole added at the origin. That's g of S over S. That's all it is I've now introduced one additional pole in my original system's transfer function, and that pole is right at the origin. I've divided capital G of S, which is what I started with in my system, by S. Here's where I'm going to get a little bit funny with the notation. I now need to put that into and find a G of S. I'm sorry, a G of Z. I want to now take this. I have capital Y sub 1 of S. That's the response of my system to a unit pulse. I want to now inverse Laplace transform that, find the little y sub 1 of t, sample that. That will give me a sequence of numbers that I can Z transform. And then I will have it. I will have my G of Z. Because now I've introduced, in addition to this, I've sampled that analog waveform. Or I'm trying to now find G of Z. That's going to be the following. Let me write it down and then I'll try to back my way out because I need to put it all in place, and I'm afraid I won't give myself enough room if I start with the inner piece. So the final thing that I'm going to do is Z transform. And what can I Z transform? I can Z transform a sequence of numbers. So that sequence of numbers is going to be a sampled version of little y sub 1 of t. Well, what's little y sub 1 of t? Well, that's the inverse Laplace transform of capital Y sub 1 of S. This is what I want. This is the zero order hold equivalent of G of S. This is y sub 1 of t. Whoops. Getting ahead of myself. This is y sub 1, little y sub 1 of t. This is a continuous time signal. That's the unit pulse response that results from this combination of a zero order hold and plant combination. Then I sample it with my D to A converter at the output. That's what this is. Those, do you see the sample? The dotted line, that means sample. That's the symbol that I'm using to say that this is the sample with the analog to digital converter at the output side. By doing that, all of this now, outside of the sampled, is a discrete time signal. Once I have a discrete time signal, I can Z-transform it. And that's what I'm now calling my zero order hold equivalent of G of S. Let's see if we can work through that. So this is the definition. When I write Z-transform of capital Y sub 1 of S, I'm really meaning all of this stuff. I'm inverse Laplace transforming capital Y sub 1 of S. Then I'm sampling, and then I'm Z-transforming. So by definition, I'm going to overlook all of that, all of those symbols, and just say script Z of curly brackets Y sub 1 of S. That's my G of Z. That's by definition. When I say that, I'm really meaning all of this. Inverse Laplace, curly bracket, Y sub 1 of S. That now gives me a continuous time signal. Let me sample that. Then I Z-transform that sampled signal. We can put all of those together, and it's cleaner to just look at what happens with G of Z. What do we have? We now have G of Z, in fact, is now, if we go back, do you see what I can now do? I can do, by definition, the Z-transform of G of S over S minus the Z-transform of e to the minus capital TS G of S over S. That's the notational convenience that I'm suggesting you believe or buy or accept in this process. Now I simply need to do two Z-transforms, one of G of S over S and one that's been delayed by one sample, e to the minus TS G of S over S. Or G of Z is now the Z-transform of G of S over S minus the Z-transform of e to the minus TS G of S over S. But the right-hand term simplifies. Yes? So now I'm absorbing all of this notation. I'm simplifying it and saying, by definition, I'm now replacing all of that mess. If you just give me a G of S over S, I'm now saying, instead of saying inverse Laplace transform, G of S over S, sample it, then inverse, and then Z transform, I'm just saying, just do this one step of the notation. Z transform G of S over S. If that's okay, what can you tell me about e to the minus TS? What is that the Laplace transform of? Note that e to the minus ts is the Laplace transform of what? Or what does that represent? E to the minus ts, if you saw that somewhere in a Laplace transform derivation, what would you associate that with? A delay of capital T units of time, which is really capital T is one sample period. Note that e to the minus capital Ts is the Laplace transform of a delay of t seconds. And what's the z transform? Of a t second delay. A t second delay is a one sample period delay. How do we write that in the z domain? Z to the minus 1. So now the z transform of a t second delay is z to the minus 1. Ha. Now do you see what we can do? We're trying to z transform a z to the minus 1 in that second right-hand term. We can factor that out of the z transform, and then we have two z transforms that are the same, g of s over s. Let me write that down. So now this implies that g of z is in fact the z transform of g of s over s. Again, this is the zero order hold equivalent of this combination of zero order hold combined with a plant, where our plant is g of s, minus z to the minus 1. Ha, I've gotten rid of that irrational, bad-looking e to the minus ts by factoring out the z to the minus 1, z transform of g of s over s. And that now says that if I want the z transform, the zero order hold equivalent of a g of s, I can now produce it. I multiply the z transform of g of s over s with this factor, 1 minus z to the minus 1. And now I have a zero order hold equivalent of the original system g of s. And g of s over s, just put one more pole in that g of s transfer function and you have it. And that pole is right at the origin. Here is our zero order hold equivalent. So now if somebody says, give me the zero order hold equivalent, or they might, in a different source, a different textbook, a different reference material, they may call it the pulse response transfer function. That's this. You now need to z transform g of s over s and multiply it by 1 minus z to the minus 1. And we can rewrite that 1 minus z to the minus 1 in terms of positive powers of z, because that's 1 minus 1 over z, or that's the factor z minus 1 over z. But for consistency with a lot of sources, this is how you might see it described. Zero order hold equivalent, boom, it's this. Let's now do that for some examples. Let's look at a zero order hold equivalent, example 1 of a pure gain. Suppose the plant, g sub 1 of s, that's the g of s that we've been talking about, is just a constant. You give me an analog signal, and my plant simply amplifies that signal by 5. If that was a cosine of 2t, the output is going to be 5 cosine of 2t. That's all my plant is doing, is scaling the signal, the input signal. What's going to happen? What's going to be capital G sub 1 of Z. What's the zero order hold equivalent of a pure gain? What's the pulse response transfer function? I'm now trying to put all of these pieces together where G sub 1 of S is now, it doesn't have any dynamics, it's just a gain. That's about as simple of a system as you can have. It just scales the input. So this is just a gain. Can we now find capital G sub 1 of Z? What did we say the formula? Question.
So G, I'm sorry, this is just more of a notation question. I forget. So G sub 1 of Z, is that, why is that different from G? Like what's the sub 1?
So sub 1 just means this is my first example for you. So this G sub 1 of S is actually G of S that I've been talking about all night. I've just now subscripted it so that you can tell it from the next example, which will be G sub 2 of S. Is that okay? So the G sub 1 means nothing other than this is one example, the next one's going to be the second example, G sub 2. The next one might be G sub 3. If we keep going, if we go until 11, it'll be G sub 5. Okay? And I know everybody's just dying to stay here. You'd have nothing else to do this week, since everybody's put something on you probably before spring break to be done. What is G sub 1 of Z? What's G of Z, really? Expression-wise, what was the formula that we just wrote down? We just put this down. So now we have G sub 1 of Z is 1 minus Z to the minus 1 Z transform of, and since it's the first example, it's G sub 1 of S over S. Let's now plug in what we know. 1 minus Z to the minus 1. Let's not change that yet. Let's just keep that the same. But now we actually know what G sub 1 of S is. That's a constant. That was 5. Let's put that in. This is now 5 over S. And now we can actually, and I'm going to break this down into a lot of different steps. Another reason why we might be here until 11. But the 5 I can pull out. That's just a constant. I can now say, oh, this is the same as 5, 1 minus Z to the minus 1, Z transform of 1 over S. And you actually might see a table that has the Z transform of 1 over S. Boom, now you just plug that in. But, in fact, what did we say is going on behind the scenes? We have to inverse Laplace transform that, sample it, and then Z transform that sampled signal. Or if we just kind of wrote it down notation-wise, what's the inverse Laplace transform of 1 over S? U of t, but that's just 1, isn't it, for all time. So now we are just sampling. So this is now what we're effectively doing in this next step is we are sampling a unit step response waveform. Or, in fact, this is what we have. And you can Z transform that. That's 1, 1, 1, where this is t, 2t, 3t. Or we could now say, oh, you know what? This capital G sub 1 of Z, let me just rewrite it. of the Z transform of 1 over S. And in fact, instead of going through this inverse Laplace sample, we will just say, you know what, let me find this in a Z transform table. I just happen to have a Z transformed. And this may look different to you, but this is now under exam number 2's material. This is a different table, but you need to get comfortable looking at different sources, so I'm giving you a second table. Can you now find in the capital X of S row something that looks like 1 over S? Yeah, row 3. Row 3, and I show you 4 fingers. Row 3, I can't see, so I'm hoping you can't see either. Well, if you're listening to this, you can't see either, but luckily. What is the Z transform then of 1 over S? 1 over 1 minus Z to the minus 1. So this table actually gives you Z transforms in terms of Z to the minus 1s. And you could derive that. You know how to do that. Do the common ratio, take the difference of those 2 rows, get rid of the tails that match, and you end up with 1 over 1 minus Z to the minus 1. We could now say, oh, let's go back. Oh, really? It reset. I apologize, but close your eyes if this makes you sick. We now can say, oh, this is now corresponding to row number 3 in the Z transform table. For exam number 2. And in fact, that table has transforms and properties. It's 2 pages, and you'll be allowed to bring both pages to exam number 2. In addition to an additional sheet of notes. So you now have 2 front and backs, plus a 2-page Z transform table if you would like, if this one makes you feel better. So what do we have? Now we can put all of these pieces together. G sub 1 of Z is now 5. What's this? This is now 1 over Z, but I can put that all over a common Z, and this is now, or maybe I don't want to do that. Well, yeah, let me, do you see that's okay? And this was what? This was 1 over 1 minus Z to the minus 1, which I could multiply both top and bottom by Z and end up with Z over Z minus 1. That's that. And this is that. We okay with what I've done? The Z transform of 1 over S was in row number 3 in the new Z transform table, and that was 1 over 1 minus Z to the minus 1. I can multiply that by 1 to produce Z over Z minus 1. And what happens? This is that chalkboard that you see in the comic, and it says magic happened. Actually, this is magic, and you can see it. The magic is right there in front of us. The magic is we get to cancel. We get to cancel common terms. We can cancel the Z. We can cancel the Z minus 1. And what happens to our zero order hold equivalent of a constant? We get that constant. And that kind of makes sense. We have a constant. That's our dynamic. It really has no dynamics. We zero order hold, and we get a transfer function that's that same exact constant back. So this seems to make sense. Okay, let's step it up a notch. Suppose now we want to have the zero order hold equivalent of a pure mass system. That's now G sub 2. G sub 2 of S is the dynamics associated with a pure mass. That's our system, G sub 2. What's the free body diagram of a pure mass system? So now I know this is reckoning back to physics, oh my, physics 141 maybe, mechanics. And I heard at lunch today that somebody just loved their physics classes. All of them, right? Best 3 classes that you've ever experienced. Now I'm feeling really hurt. All right, so here, what's the free body diagram of a pure mass system? We have a mass, and it's a pure mass. There's no spring, there's no dash pot, it's just a mass, but let's apply a force to that. Let's now hit that with a force, which we will, I hope now by context you know what I'm doing. U of t is not the unit step. U of t is our force input. That's our generic force now. U of t is a generic input. This is our force input. And we probably want to draw a line in the sand and say there is our position x, and relative to that we can talk about the velocity. What's G sub 2 of S? Let's go sit under an apple tree. Right? Let's just pretend we're Newton. What does that mean? F is equal to MA. And what is A? Stands for apple. No, A stands for acceleration. And acceleration in terms of x is x double prime. So, our from physics, I know this is making you weak in the knees. I'm going to have to pull a chair up here in a minute. But now from physics, we know that F, which I'm calling U, is equal to mass times acceleration. And now I just changed notation. So let me make that a dot here. Since I'm not worrying about current, x double dot is the acceleration. So this is now, from physics, this is now our force is equal to mass times acceleration. And we want to now convert that into a capital G sub 2 of S. We now need, the input is our force, that's U of t, and our output is x double dot. Let's solve for our output. X double dot is equal to, we can divide both sides by capital M, U of t. And that 1 over m might seem a little ugly, so let's go Greek. Let's just replace 1 over m with a Greek variable, alpha. Where this is now just a constant. What's the transfer function of that system? And when I say transfer function, what can you immediately be thinking if I now want to Laplace transform this differential equation? This is a linear differential equation. It's second order. It's a second order differential equation. I want to Laplace transform it, and since I'm saying transfer function, what immediately goes off in your head? I don't need to worry about initial conditions. So now my ICs are 0, which allows me now to quickly, cleanly What's the Laplace transform of the second derivative of x? What's the Laplace transform of the first derivative of x? What happens when you differentiate? What's the equivalent to differentiating in the time domain and its Laplace operation? What do you do in the Laplace domain to differentiate in the time domain? Multiply by s. Now we are differentiating twice. We multiply by s once, s a second time. The Laplace transform of the acceleration is now s squared capital x of s. And what's the Laplace transform of the right-hand side? That's just the shift key. We're just Laplace transforming little u of t. That's just capital U of s. So this now becomes alpha u of s. Or capital X of s is now alpha over s squared, dividing both sides by s squared, u of s. And this, hiding in plain sight, is the capital G sub 2 of s. That's our plant now that we want. The Laplace transform of a pure mass is now equal to alpha over s squared, where alpha is just a constant. Who knows why that's there? Let me get rid of that, because we just found it. We just found the transfer function. That's alpha over s squared. What's the zero order hold now? We want to find the zero order hold equivalent of G sub 2 of s, which really is just a double integrator. We're integrating twice. That's a pure mass system. We want to now Laplace or zero order hold equivalent this G sub 2 of s. What's G sub 2 of z? If you were looking for partial credit, good luck on the multiple choice. But anyway, G sub 2 of z is what? What's the formula? In terms of G sub 2 of s, can you write it down? The zero order hold equivalent says, oh, I have 1 minus z to the minus 1, z of, in terms of G sub 2 of s, is now that. Well, that's now 1 minus z to the minus 1, z transform of, plug in G sub 2 of s, alpha over s cubed. Now I simply need to find a 1 over s cubed in my Laplace transform table, and I'm done. That's 2 over. Do over, 2 over. Ha! I didn't lift my pen, so I could easily erase that. But now if it's 2 over, do you see you would just divide what's in the transform, or both sides of that row, by 2 to get 1 over? We have alpha. We could pull the alpha out. But now we can say, oh, that now looks like that. That's the z transform of 2 over s cubed. Well, let's go back a little bit before. Oh, I'm glad it didn't go all the way back. But we can now recall that the inverse Laplace transform, if you looked at one of those intermediate columns, that's now t squared over 2 factorial. And in fact, if we now write down, using what we just saw in that transform table, We divide by 2, and we had an alpha, so it's alpha over 2. And now from that column of z transforms, that was this t, capital T, z plus 1 over z minus 1 cubed. And I think that was row number 6 of the z transform table from exam number 2. This now is z minus 1 over z. Do you see we have a little magic going on, or a little cleaning up to do? We can now say that g sub 2 of z, this z cancels that z, this z minus 1 cancels one of those, and we're left with alpha over 2. Let me put the, wait a minute. My memory was failing me. That was a capital T squared, since it was a little t squared. This is alpha t squared over 2, z plus 1 over z minus 1 squared. And this is what? That's the zero order hold equivalent of a pure mass. And what I may do after I turn off the recording is go through an example and say, what if my mass is 1? What does that look like? But do you see where your poles and zeros are in the z-plane? You have 2 poles at z equal to 1. And what did you have for a double integrator? In the S domain, you had 2 poles at the origin. That looks consistent because we know things go through this e to the minus st mapping. I'll add a little bit more. I haven't gone quite to 11. 2 minutes instead of 4 hours. But thank you for your patience. We will pick up beyond this in the next lecture.